Okay, so like I said, it took forever to prepare for this lecture. Uh, 2 months almost fully dedicated, reading these four books and several other papers by History of Mechanics, René Dugas, History and Philosophy of Fluid Mechanics, Grigori Ducati, the Historical Development of Aerodynamics, von Karman, and some collections of the early pioneers. And yet it's far from being complete. I thought at the beginning that fluid mechanics is just a branch of mechanics, and as you guys know, we already have a lecture on history of mechanics before, so I thought it will not be that hard of a job. But you know, um, I find myself swamped into a very rich and long history of fluid mechanics, quite independent of mechanics, with its own tools and stories. Yes, fluid mechanics is branch of mechanics, but by the early 18th century, with names like Newton, Bernoulli, Dalembert, Euler, among others, it rapidly became an independent branch of science. And not only that, there is another branching happened around early 20th century, the era of flight, by names like Joukowsky, Kotta, Lanchester, Prandtl, von Karman, among others. So now we have aerodynamics is actually an independent branch of science. So to summarize, this evolution in one lecture was not possible. So there are going to be two lectures, and this was quite challenging. Going to be two lecture, one today on you can say pretty much on fluid mechanics, and the next one will be on the aerodynamics and theory of flight. So having said that, we should ask why should we study history of these things? I mean you will find some of these concepts are really immature, and now we know better. I'll give you my own opinion. So I study these things. When we learn about these great names, when we read about their personal stories and criticism of one another, we tend to bring them down from a godly status to a human status, so that we have the audacity, the boldness to criticize, to propose extensions. And if we keep doing that over and over again, discreetly, we will reach that level. So when we study history, it's always challenging to determine where to start, because it implicitly assumes that there was nothing before, and this is of course not correct. But at any rate, everybody knows that the ancient civilizations, Egyptians, Chinese, Indians, Persians, they had great development, and of course they knew something about fluid mechanics. And since I come from Egypt, I will take the opportunity and give little bit about the Egyptian civilization and their relation with fluid mechanics. It's a civilization that lasted 4,000 years on the banks of the Nile River, one of the greatest and biggest rivers in the world. So it's hard to believe that this civilization was not aware of fluid mechanics basics. We have evidences already that they recorded the yearly risings of the Nile, because each year, each season, the flood comes and wipes out lands and destroys buildings on the banks of the river. So each year was a lesson to them. So probably they learned it that the narrower the channel, the higher the speed, several thousand years before Da Vinci arrives at the same rule. We already know that they built boats and ships, and we also know about the water clock, by regulating the input flow and outflow here out of the small hole at the bottom of the conical shaped tank. The amount of liquid here in the tank, or actually the collected one here, either would represent time, so you can calibrate this with the daylight to get your time. And interestingly enough, several thousand years later, Galileo used a very similar setup to measure time during his experiments. So that's enough of an introduction, and let's go a little bit more serious. The Hellenic period. So because we know much more about the Hellenic period than the ancient. almost everything is recorded. So in the Hellenic period, there is one man that must be mentioned, which is Aristotle, and I'm going to skip his contributions here because they are rather on mechanics in general, not fluid mechanics in particular. And if you're interested, you can watch our lecture on the history of mechanics. But there is one man, if we talk about the history of fluid mechanics, and there is one man in the Hellenic period that cannot be skipped, because simply his name exists in every single textbook fluid mechanics, and that is Archimedes. So he wrote two books, one on the center of gravity and another on floating bodies, and of course we're here concerned more with the latter, where he developed very important fundamental concepts in fluid mechanics. For example, the continuity concepts, that fluids cannot have internal empty spaces. It's due to Archimedes. And based on this concept, he developed the following, and I'm quoting: if fluid parts are continuously and uniformly distributed, then that of them which is the least compressed is driven along by that which is more compressed. So he's now alluding to the fact that fluid flow is driven or can be driven by pressure difference, and also the flow goes from the high pressure to the low pressure. So this concept we owe to Archimedes. He also postulated that equal weights of fluids at equal distances from the center of the earth are in equilibrium, and using this principle, he arrived at the following: that each part of the fluid is compressed by the fluid which is above it. So that the pressure or the weight goes with the depth, rho gh kind of thing. Again, this we also owe to Archimedes. And of course, the very famous one, he has several propositions about buoyancy, and this is the one that is indeed in every textbook of fluid mechanics. The rho gv kind of buoyancy force and the concept of displaced volume. And this always comes with the famous anecdote that everybody loves to tell about the Eureka thing, where the king of Syracuse asked him, to determine whether a given crown is made of pure gold or has some silver in it. And he used these concepts to determine the volume of the thing, of a given mass, through the displaced volume, and as such arrive at the density and compare it to the density of a gold. So anyway, everybody loves to tell this anecdote, and there is a lot to say about Archimedes, but we don't have time. So we have to go to the serious thing, and going from the Hellenic to the Renaissance, you always, there is something you recognize and realize whenever you read about the history of science, whether it's history of mechanics in general, history of fluid mechanics, philosophy, or whatever, is that the dark age was really dark. In the sense, we were talking about great names, minds, thinkers, philosophers in the Hellenic period. We already mentioned Aristotle, Archimedes, Euclid, the father of geometry, hero of Alexandria, many names. And then all of a sudden, complete silence for 10 centuries. So that's true, of course, if you focus on the western part of the world. On the other side of the planet, things were not as dark. So actually, Arabs and Persians were really shining at the time in many domains: math, chemistry, medicine, mechanics, etc. And since we are in the quarantine time, this word in particular actually goes back to the Arabic polymath, Ibn Sina. So, since we're talking about fluid mechanics, let's just focus here on fluid mechanics. I'm going to mention a few things during this period. The Persian windmills, Abbas ibn Firnas, these are the first trials of unpowered flight, and it's kind of a bit shameful that is not mentioned in any of the books talking about history of flight. Al-Jazari water rising machine, and many other contributions. I'm not going to waste the time of this lecture, so I will refer you to this very interesting series, a British series, 1001 Inventions of the Arabs and Persians at the time. And let's do let's follow the books that I'm summarizing and jump ahead to the Renaissance. And there is one man in the Renaissance that, presented himself quite prominently, and that is Leonardo da Vinci. So actually, Toccati, I'm quoting from Toccati here, he said, Da Vinci was not only the great figure of the Renaissance epoch, but also the most gifted among thinkers, engineers, scientists, and combined in one person. in the entire history of civilization. And when I read this, I said, oh, wow, that's too much exaggeration, particularly because others have, you know, softer and softer tones about Leonardo da Vinci. Like Dugas, for example, he said, Leonardo da Vinci cuts the figure of a gifted amateur. And then you wonder, is he amateur or a scientist? So the thing is, in fact, the thinkers and philosophers at the time, they actually denied him a place amongst them. They didn't consider him as elite, you know, as a thinker and philosopher, because he lacked formal education in Latin and mathematics. It seemed that this, you know, demoralized him a little bit, in the sense that he used to actually call himself senza lettere, which translates as without letters. So some people debate whether he really meant without letters, the one who cannot read, illiterate, or the outsider, that he's outside of this elite group. And this is quite disheartening because, you know, Leonardo da Vinci, as you're going to see in a minute, he really achieved a lot in too many areas. And it's sad to know that he was a bit demoralized at the time. So let's see if he is really scientist or an amateur. Let's get some of his own quotes, his own words about how important theory and science is. And in fact, some of these, you know, are very good candidates as preface for books, preludes for, you know, talks and presentations. If you want to look, you know, better educated person, to have like a quote of Leonardo da Vinci in your talk or something, it's quite interesting. So here are some of his quotes. No knowledge can be certain if it's not based upon mathematics. And look at this. Again, I'm quoting. Practical knowledge must always be founded on sound theory. A painter must know the meaning of such notions as point, line, surface, volume. He must know that the smallest natural point is larger than all mathematical points, because the natural point has continuity. And anything that is continuous is infinitely divisible. But the mathematical point is indivisible because it has no signs. That is amazing. He is so close to the concepts of measure theory. And my favorite one, mechanics is the paradise of mathematical sciences because by means of it, one comes to the fruits of mathematics, which is actually used by our colleague Francesco Bolo at Santa Barbara in his book, Geometric Control, as the preface of the book. And there are other many, I could not include all of them actually. But I mean, when you see this, you wonder what else he could have done to convince them that he believes in science and he behaves as a scientist. He believes in theory. He's not just a practitioner or an amateur. So at any rate, let's see his contributions. So here is the first one, the velocity area law. The area times velocity is constant, and this is his own words. Wherever the river becomes shallower, the water flows faster. Toccati commented, the establishment of this law alone puts Leonardo da Vinci among the great fathers of fluid mechanics. And look at this, the second. A body moving, again I'm quoting, a body moving in the motionless air experiences as much air resistance as experienced by the same body in a motionless state, but exposed to an air motion with the same speed. So that very principle that we ubiquitously apply in every nook and cranny in fluid mechanics, we owe it to Leonardo da Vinci. And turbulence, this is his own sketches, illustrations of the turbulence swirls. About inventions, too many inventions, I cannot contain all of them, of course, here. The water mill, this is a very interesting one, about optimal shape of boats. It's important, this is his words, that the ship moves through water with the least possible resistance. Therefore, man should learn from fishes, since they live in water and are shaped to move in it easily. So we can say something like, this is the first biomimetic, bioinspiration kind of thing. And look at his illustration, quite interesting. This is his own sketches with notation A, C, and E. So C in the middle is kind of symmetric airfoil. A is reversed, so all of them, they move to the left. And E is just a composition of the two. Look at his explanation. When a body moves in water, has the configuration C in the middle, and its blunt side, if forward, fluid particles move smoothly only over the forward part of its surface. At a certain point, they cease to be undisturbed and reach violence. He means, in our own language, separation. At a certain point, the flow will separate. If the same body is moving its pointed side forward as in configuration A, the smooth flow is longer. Still, there is a violence. Therefore, it too meets resistance, although smaller than in the first case. If we have a body like configuration A, water particles will remain in smooth motion throughout the whole length. Therefore, water resistance will be still less. So let me say here. So there are several things that can be, drawn from this exhibit. First, he is relating resistance, drag, to smoothness of the flow and separation. Second, he is trying to maintain smooth flow over the entire body length. So this is, this is before Navier-Stokes equations. This is before even Euler and Bernoulli. This is before even F equals ma. This is in the 15th century. So this is indeed amazing. He has several other inventions: flying machine, air screw. This air screw is quite interesting. So you have like 4-6 people here, and they rotate, re-rotate these, circular wings, if you want to say, and this thing will screw up in the air. So you can say this is the genesis of a helicopter. And indeed, Sikorsky, said that he was inspired by this sketch of Leonardo da Vinci. He came up with the concept of a parachute. He came up with too many things, to the extent that Ducati at some point he said, could he be real? Yes, he was real, and here he is before your eyes. And I have to stop here because, there are too much things to say about Leonardo da Vinci. Let's go towards seriousness. The formation of classical mechanics. There is Stephen, and I'll jump to Galileo. So Ducati actually said the following, that Galileo laid the foundations of general dynamics, without which there would be neither fluid mechanics nor mechanics generally. And this is quite true. So his contributions in fluid mechanics are not that too many, but he's generated mechanics. And I will skip, of course, his contributions to mechanics. You can find them in our lecture on the topic here. For fluid mechanics, if I'm to mention only one thing, I will mention this. So he showed and proved that the pressure at any point depends only on the head, the depth. And this concept we know from before, from actually the time of Archimedes, and also Stephen stated it quite explicitly, but Galileo proved it both experimentally and mathematically, and this was his usual trait. He was a true experimentalist, and he was also the chair of mathematics department at the University of Pisa. So this is why he was so unique. He had both. Nowadays we have experimentalists and theoreticians. They fight together, and they both fight computational people. So this is why he was so unique. So the word head, pressure head, we owe it to Galileo. Torricelli was one of his disciples and students. He's famous of his Torricelli's experiment. And actually, I didn't remember that I did it when I was a child at school. So I actually went to the kitchen and did it. It was quite interesting. So anyway, you can see the Torricelli's emptiness, which proved the existence of vacuum, because the Aristotelians thought that there is no vacuum and nature abhors vacuum, is one famous saying. But more importantly, he came up with the concept of a manometer to measure pressure. And he's also famous for his law, Torricelli's law. Let's look at this story. So Galileo was doing these kind of experiments, hundreds of times. I'm not exaggerating, really 100 of times. So a ball rolling on an inclined plane. Okay, so he wanted to measure time, the time of the excursion, the time taken by the ball to go from here to there. Okay, how he can do that? He used a concept very similar to the water clock. We have a tank here full of water, and we have like an opening here. At the beginning of the experiment, he just opens the hole, and the collected water here, he collected in a bucket or something, the collected water, the weight of it represents time. So that's okay. And since Galileo did it over and over again, Torricelli saw this experiment over and over again many times, so he decided to determine try to determine a law governing the velocity of the discharge. And here is the law that everybody knows, square root 2gh. And of course he didn't write 2g kind of thing. He established the fact that the velocity is proportional with the square root of the height. And you can see it's actually, he arrived at it from a purely mechanistic point of view, in the sense that the same law applies to also particles. If you have a particle and loses this height, it will gain the same velocity. It's just a conservation of energy. The Torricelli law is important because of the following. So two things actually. So first, before this law, almost everybody was talking about hydrostatics, equilibrium. Now you can see we're talking about hydrodynamics now, and indeed he is characterizing the velocity of the motion of the fluid. So this is from one point of view. From another point of view also, in fact, this equation, we will see in a minute that this was fundamental in Bernoulli's derivation of his very famous equation. Pascal, one important thing is that he established the following principle, that the pressure, at any point is the same in all directions. And since pressure depends on the depth, it must be lower at summits of mountains. And he came up with the concept of a barometer to measure, the atmospheric pressure. He is also famous for this paper where he, showed the existence of a vacuum. I'm quoting, "Nature doesn't avoid vacuum with as much horror as many imagine," because, the Aristotelians, they thought that nature abhors vacuum. He is famous of his hydraulic press, and in this connection, actually, he defined the word pressure. So everybody before him was talking about the weight of the liquid. Now he's talking about a pressure, and he said that the pressure is the same beneath the two pistons. And the Pascal principle is that the pressure is transmitted without losses in incompressible fluids. Now we are in the heart of seriousness. This is Newton, and indeed Toccati's statement about Galileo that he laid the foundation of general dynamics, without which there would be neither fluid mechanics nor mechanics generally. This indeed applies perhaps even more to Newton. So again, I will skip his contributions to mechanics. I'll focus on his contributions to fluid mechanics. And in proposition 33, section 7, book 2 of Principia, like his masterpiece, the Bible of mechanics, he provided this proposition: the fluid force acting on a body is proportional to square of the velocity of the body moving, square of the linear dimension of the body, so area perhaps or something, the density of the fluid. And he arrived at this proposition based on the following concept, that the force acting on a body can be either, so the force acting on a body is coming from the fluid, so it's the opposite on the fluid. So now he's talking about the force on the fluid. It's either centrifugal forces due to deflection of the fluid particles or impact of fluid particles. And when I saw this, I was quite interested, because the first one is quite deep actually. So remember, everybody was talking about impact, and impact was very well studied at the time between either particles, or even nowadays, like beginners of fluid mechanics and aerodynamics, sometimes they think that when a wing moves in the air impinges into the wing, pushing it backward and upward, and the lift is due to impact. And this, you guys know, it's not correct, right? The lift is indeed due to the first category. The lift lies here in the first category. It's due to deflection of the fluid particle. It's a centrifugal force, and actually there is a very like a recent paper. I can refer to you later on, that shows that the lift is kind of a centrifugal force. So it was interesting to see that Newton arrived at this statement. Of course, he's not talking about lift or anything. So he developed two theories of fluid and fluid resistance. I'll skip the first one because it's incorrect. Actually, both are incorrect, but he himself corrected the first one. So the second theory, he proposed the following, that a stream of fluid is composed of a continuous chain of particles, but they can move relative to each other. And if one part of the fluid moves, this motion gradually communicates to the rest of the fluid. This is in contrast to his first theory where he said no, they are independent. Now he's saying no, they are not independent. If you move one part of the fluid, this motion will communicate to the rest. And this is very important because this is he's alluding to viscosity kind of thing. He actually, he literally said this, that this is due to defectus lubricitatis, or what we may translate as lack of slipperiness. So he's alluding to viscous effects. Okay, so in proposition 34, he determined the resistance on a solid cylinder. And let's look at this. He's saying that this resistance on a cylinder moving in a fluid is given by the weight of a fluid cylinder of the same base as the solid cylinder and a height equal to half the height of a body. Half the height a body would have to fall in order to acquire the same velocity of the solid cylinder. And this is quite interesting. I mean, when you read in history of mechanics, you encounter these kind of statements and writings over and over. It's kind of everything they're relating to gravity. Everything they're relating to gravity. It's as if this is the only force that they know about. So if they want to mention a height, if they want to describe a height, they describe the height that a body would take to fall. If you want to describe the time, they would describe the time during the fall from point here to point there. You know, this is their common language. He stopped here, Newton. But if you take these concepts and apply to a flat plate moving with a speed with an angle of attack, apply the same concept. So again, Newton didn't do this. So now you use the same approach, which means that particles move in a straight lines until they impinge on the body. They lose their momentum in the normal direction. So you get force in the normal direction, and the force you can simply very easily show that it's just given by this law, u squared and sine squared alpha. It's called the sine square law. And this is, of course, this is not correct, okay? And actually some people blame this relation for delaying the development of flight, because this relation provides very small lift forces at small angles of attack. So you need to go very high angles of attack to get lift, and at these high angles of attack, the drag would be immense, would be huge in comparison to lift. The drag to lift ratio would be very high. So okay, that's okay. Newton established mechanics. F equals ma. We have principia. We have governing equations in general, and now fluid mechanics start to be the branching of independent fluid mechanics, starting with Daniel Bernoulli, the first textbook in the field, Hydrodynamica, 1738. And so, like I said, this is perhaps, this is his own words. My theory is novel because it considers both the pressure and motion of the fluids. It might be called hydrolocostatica kind of thing. So yeah, he's the first to establish a relation between pressure and velocity. And his analysis was based on the conservation of living forces. For those of you who have taken dynamics with me, you guys know that the living force is just Leibniz vis viva, which is kinetic energy in our common language. And at the time, there was a polemic fight in the community whether this is really a quantity of motion, is it really conserved during motion or not, and when Bernoulli was proposing this, he was quite cautious because the fight was at the time. He was cautious to say that this is based on conservation of living forces. So he was trying to say, no, you can also recover it from Huygens principle, this or that. And the community fought actually back. They were not convinced of the conservation of living forces. They wanted to rederive his equation using other principles. So Maclaurin, Jean Bernoulli, and Dalembert, they tried to rederive his equation from starting from other principles, and yet they arrived at the same equation. So this was quite interesting. For those of you who are interested in knowing something about this fight, this is again another lecture. It's not the history of mechanics, it's the principle of least action. Okay, so let's go to his work. This is chapter 13 of his book, and his objective was to determine the pressure in the horizontal pipe BD. Okay, so let's see his philosophy. He's saying the following. If we have this height A, I'm using his notation. So by Torricelli's law, the discharge velocity is the square root of A. And there is something interesting here. So when you read the history of mechanics, you will find the pioneers always took equality when it's really meant for proportionality. So we know that Torricelli's law stated that the velocity of the discharge is proportional to the square root of the height. Okay, they took it equality. And that's okay because, you know, when we grow up, we start to add, you know, coefficients and stuff like to adjust units, for example. But I just like to tell you something interesting, that this also applies to our most fundamental law of mechanics, force of equal mass times acceleration. Indeed, in Newton's, you know, writings, he stated that the force is proportional to, or defined as the proportional to, change in momentum. And in his analysis, he took the equality. So that's interesting to, you know, that our most fundamental principle that we apply in every nook and cranny, it has some arbitrariness in it. So you could have defined the force to be 4 mass times acceleration or 3.5 mass times or whatever, you know. It doesn't matter, of course, right? It doesn't matter. And actually, there is an interesting quote somewhere in the book by Ducati that the question which has been encountered by every scientist and philosopher throughout the entire history of civilization: what is force? And I'm leaving it at that because it's not my point here. So let's go back to Bernoulli. The discharge velocity is square root A. There was an orifice here, so it's narrower than the pipe. The ratio of the area is N. So by Da Vinci's velocity area law, we know that the velocity here will be smaller, right? You divide by the area ratio. So now the velocity of the pipe is smaller. And so if he said the following, this is his, you know, approach. He said, if we cut the orifice, now the pipe is connected directly to the discharge, and Torricelli's law implies that the velocity of the discharge is square root of A. The velocity of the pipe now is smaller, so this means that the flow in the pipe has the tendency to accelerate, but the orifice is preventing it, thereby compressing it, creating a pressure on it. So he said that the pressure is indeed proportional to the acceleration of the flow in the pipe if we cut or if we remove the orifice. So this is what he said. He said, okay, I'm going to remove the orifice and compute the acceleration of the flow in the pipe, VdV by dx. This will give me a measure of the pressure. So this is the equation that he indeed arrived at. Has nothing to do with P plus 1/2 rho V squared that we always use, okay? But of course you can recover this from his equation. So you can, you know, recognize that the left-hand side is the pressure, right? Because he said the pressure is the acceleration. And the right-hand side, we have the first term is N squared goes away, and we have A is the height. And the second term is A over N squared. This is indeed the velocity in the pipe. So from this equation, you can write something like P plus V squared equals H, or if you add units, if you adjust units, you will have P plus 1/2 rho V squared equal rho GH, which is the Bernoulli's equation that is one of the most famous equations in fluid mechanics. But like I said, this is what he derived. It's not the final form of Bernoulli's equation, and this urged Ducati to ask who then derived the famous form of the Bernoulli's equation. And he kept searching and searching, and we will see later that it's indeed Lagrange, it's not Bernoulli. And this reminded me of an interesting saying, a sarcastic principle by Vladimir Arnold, a contemporary mathematician who passed away 10 years ago. He's a Russian mathematician, has original contributions in theoretical mechanics and fluid mechanics in particular. He has this sarcastic principle that If an ocean bears a personal name, then this name is not the name of the discoverer, period. So if you have this equation called Bernoulli's equation, then it's not Bernoulli who came up with it. So that's quite interesting. And actually, one of Arnold's students, he said that Arnold principle applies to itself. So that was also another interesting fact. Okay, enough with Bernoulli, and we will go to Dalembert now. As you guys know from the course of dynamics, that he reduced the entire science of dynamics to statics. Everything to him is equilibrium. And here is a paper studying the equilibrium of fluids. And he made this assumption. Look at this. The velocity is uniform across slice perpendicular to the flow, and that the parallel slices remain parallel. You can imagine how confining this is to his analysis, and I believe that this is really behind the Dalembert paradox. So, like I said, he tried to rederive Bernoulli's equation from. He was not convinced of the conservation of the living forces or kinetic energy at all. He wanted to. To him, this was not a principle. This is something that needs to be checked every time. And here is his own words after he arrived at Bernoulli's equation. Therefore, it is seen that the principle of conservation of living forces also applies to fluids. And indeed, I am forced to confess that the results of my solutions always agree with those of Daniel Bernoulli. Then the Academy of Berlin, they made a competition on the resistance of fluids. We have Newton's theory, and they wanted, there actually was not only Newton's theory, there were several theories, and they were contradicting. Newton is perhaps the most famous. So they wanted a competition in that domain. Hey folks, go and try to analyze the resistance of fluids. And they stipulated experimental validation. And nobody won the competition. So there was no awards. And Dalembert actually participated, and he didn't like this decision because he was upset that the theories were contradicting and no time to divide one's focus and attention between theory and experiment. He tried to develop a very rigorous theory indeed. So at any rate, he collected his writings and published a paper in 1752. So Douglas describes it as his analysis is so long and tortuous that we cannot attempt to summarize it. Toccati also said, but the results of his almost heroic efforts were so complex mathematically and so far above the grasp of the average reader that they had little impact on the further development of fluid mechanics. And this is quite interesting to us as beginners in the field, in the sense that he was a really, if you read his stuff, first of all, I agree with these statements. Of course, I tried to follow his analysis. I couldn't. It's very hard to follow, okay? Second, when you read to Dalembert, he's really a philosopher of a kind. And it's sad that, of course, he preceded Euler by at least 10 years developing equilibrium equations for fluids. And come on, Dalembert is equilibrium. Equilibrium is Dalembert. He reduces the entire science of mechanics to equilibrium. Of course, he's expert on equilibrium of fluids. But it's clarity. It's clarity, guys. It's clarity. It's not, no matter how good you are, how smart you are, how deep thinker you are, it is clarity. So you can see Lagrange descriptions about Euler's presentation of hydrodynamics is direct and luminous. This is why they lasted centuries and centuries. It is clarity. I cannot make it clearer than this, right? Okay. So, but there is one part of his analysis that I really liked, and I thought it's relevant. I want to bring it up. Here it is. If the solid is not terminated in a very sharp point, in such a way that the derivative dy by dx may be either finite or infinite at the origin. So the origin here is a point on the body, is the starting point of the body. He's saying if it's not sharp, so if it's, we have a finite slope kind of thing, or it's just a wall, so it's infinite slope. If this is the case, there will be, or there may be, a small portion of the liquid which is stagnant at the front of the body. But in order to avoid this difficulty, I suppose dy by dx equals 0 at the origin. so that the point of the body is infinitely sharp, that there will no longer be stagnant fluid. It was quite interesting to me to see that he is relating stagnation to sharp edge and this kind of concepts. He is not alluding to Kotta condition or anything, but it was quite interesting to bring it up. And this is his famous result at the same paper, that at the end he arrived at, or he found that the pressure in the forward surface is equal and opposite to the pressure in the backward surface. And he concluded it will follow that the body will suffer no resistance from the fluid. And his famous statement that I must therefore confess that I don't know how the resistance of fluids can be explained by the theory in a satisfactory way. On the contrary, it seems to me that this theory, handled with all possible rigor, yields a resistance which is absolutely nothing in at least several situations. I bequeath this strange paradox to the geometers that they may explain it. This is then Dalembert paradox. And there is something I'd like to point here. Look what he said. He's asking the geometers to may explain it. So you encounter this word over and over again. Many times when you read the history of mechanics, everybody is talking to the geometers. I posed this problem to the geometers. I asked the geometers of the time to do this or do that. So indeed, it was geometers who concerned themselves with mechanics, and the relation between mechanics and geometry is indeed longer and older than we might expect. With all these advancements, we have Newton theory contradicting other theories, including Dalembert about the resistance of fluids. We need experiments. So Mario did some experiments on flat plate and moving water. I'm going to skip it and focus a little bit on Borda's experiment. Some people, describe him as father of experimental aerodynamics. He has this funny quote that fluids are more sophisticated than the most sophisticated lady's character. It's no offense here, but I thought it's funny to bring it up. He made a detailed study of orifices, and he showed separation behind corners. Some people call this as Borda's theorem, but this is his experiment that he's famous for. It's kind of a whirling arm concept. So he has a weight here. As this weight goes down, it rotates this pulley, and as this pulley rotates, it rotates the object, the test, the specimen that you want to test. So he's now experimenting a sphere, for example, moving in this liquid in water or something, and you can do it in air. That's fine. So it's a whirling arm kind of thing, and actually this whirling arm concept was proposed by Rubens, several years ago. He was a meticulous experimentalist in the sense that he corrected for the friction of the flywheel and the pulley, and he ran the experiment without the object and with the object, and to get to see the difference. He also waited until a uniform motion is established, so he was cognizant of the concept of transient. And finally, this is one of his famous results, that the total resistance of a body composed of several shapes is not the sum of individual resistance. We have something like fluid mechanics interference. So this was the genesis of it. And he said, yes, it's proportional to u squared and sine alpha, it's not sine squared. And in that paper, he particularly compared with Newton's theory. And this is his conclusion. The ordinary theory of the impact of fluids, meaning Newton's, only gives relationships which are absolutely false, and consequently it would be useless and even dangerous to wish to apply this theory to the craft of the construction of ships. Yes, Newton had wrong things, and Dalembert was not clear, and that's fine, they are humans. This section is quite interesting in the sense that you can use it to tease a little bit your experimental colleague. So Turgot is the minister of the Navy in Paris at the time. He asked the French Academy of Science to form a committee to investigate the possibility of improving the navigational qualities of ships. So the academy, they formed a committee. Dalembert was the chair. Condorcet and Bossuet were members. They did the experiments at the military college, and they consulted with prominent mathematicians associated with the college at the time. These were Legendre and Monge. So Bossuet did like 300 experiment towing ship models in a water tank, and this is the statement that you can use to tease your experimental colleague. He concluded that first theory, then experiment, never vice versa, for it is theory which indicates what experiment is needed. Okay, so and indeed, I mean, this was the sentiment of the committee, and this is their final report. And I'm quoting from the final report. Let's look at this. This is quite interesting, quite very important, and it's really applicable to nowadays business. They are saying this translation is by Toccati, is simpler than Dugas, though Dugas is more accurate because he's French. The whole business of experimental investigations is so delicate a matter, however, that it requires a very special attention, while in actual fact it often appears to be accidental. Information and data collected by many superficial investigators often appear to be unrelated to each other. In many cases, it is difficult to understand the causes and the sources of the data. Some forget the purpose of science. And look at their final statement here. It must be understood that scientific knowledge without reasoning, that is, without theory, does not exist. And in fact, I cannot agree more, and this can be a very good introduction of a experimental aerodynamics book. And I would also say that this is also applicable to computations as well. So let's go now from independent fluid mechanics to mature fluid mechanics now. What is that? This is Euler. And to give you an idea, Lagrange said Euler did not contribute to fluid mechanics. He created it. And this is indeed true. He wrote this paper first to analyze the equilibrium of fluids. So he recovered the equations of equilibrium that were already known before him by Clairaut and Dalembert. Then he moved the same year to equations of motion. His analysis was quite generic. Compressible, non-homogeneous, it doesn't matter. This is his problem. Given the initial state of a fluid and the external forces, determine the pressure, density, and velocity at all points and future times. Typical problem in mechanics. Applied forces, initial conditions, run your dynamics forward. So simply he's applying F equals ma, nothing more. And if you look at his analysis, I followed his analysis. It's as if you're reading of a nowadays textbook. It's crystal clear, the fluid element that you see in the contemporary textbooks, the modern textbooks. Fluid element P plus dB by dx kind of thing, and the momentum balance on the fluid element. Get the equations of motion, done. Indeed, crystal clear. Dugas said, his analysis is so perfect, is this paper, that not a line has aged. Indeed, it's as if I'm not going to say anything about his analysis. I'm not going to show it to you because you can simply go and open any textbook. This is Euler's analysis, period. And this is his comment here, from Euler's paper. However sublime may be the investigations of fluids for which we are in debt to Bernoulli, Clairaut, Dalembert, they stem so naturally from our two general formulae, meaning he's referring to continuity and momentum, his two equations, that one cannot but admire this agreement of their profound meditations with the simplicity of the principles from which I have deduced my two equations, and to which I was directly led by the first axioms of mechanics. Indeed, he's simply applying first axioms of mechanics. F equals ma, done. And he is now acknowledging how difficult his equations are. He's saying, I hope to emerge successful at the end, so that if difficulties remain, they would not be in the field of mechanics, but entirely in the field of analysis. It's not my problem. As a mechanics person, I'm done. It's not my problem anymore. It's your problem, mathematicians, analysts, and it's in the field of analysis, not mechanics. And Lagrange also says the same thing. But the discovery of Euler, the whole mechanics of fluids was reduced to a matter of analysis alone. And if the equations which contain it were integrable, in all cases the circumstances of the motion and the behavior of a fluid moved by any forces could be determined. We can solve any problem. Unfortunately, they are so difficult that up to the present it has only been possible to succeed in very special cases. And I'd like to add that it's the same thing here, right? After 300 years, after Euler and Lagrange, it is the same thing. Up to the present, it is very difficult, and we couldn't succeed except for very special cases, perhaps the same special cases that they did at the time. But there is one thing here. So Euler, realized this, and he tried to find some special cases. He indicated that if the following quantity udx v dy w dz is a complete differential, meaning it's a differential of something, it's d of something, so d of some function. In other words, the velocity field come from a scalar function, irrotational flow in our own language. There's no word irrotational back then. So he indicated that if this is the case, things would be very simple, but he stopped at that point. He didn't do analysis. How gonna simplify the analysis? In a later paper, third paper, the same year to the academy, he actually focused a little bit more on the 2D case. And he said, you know what, the 2D case, adding to this assumption of the what we call irrotational, actually Dalembert showed that the solution of this particular case can be written as u minus iv, which we now call complex velocity, is function of x plus iy, the complex argument. So, this is quite interesting because this was well before Cauchy's complex analysis, analytic functions, and so on. So now we have equations of motion, but we want a solution. Okay, we have equations of motion. We don't have solutions. They are very hard. Then came Lagrange, and as you know, guys, if you took mechanics, Lagrange is the man, right? He crowned all the efforts of mechanics in the 18th century, and to me, in fact, he is like his contributions in fluid mechanics are not commensurate with his status in mechanics. And the same applies to Newton and Galileo, by the way. He came up with the concept of Lagrangian coordinates. So instead of representing the flow field as function of x, y, z, he represents them as function of the initial positions of the fluid particle. But he himself acknowledged that Euler's formulation is indeed more convenient. Okay, so what about the solution? We need to get a solution of Euler's equation, at least for a special case. So in this regard, Ryabuchninsky, he is a very famous Russian aerodynamicist who established the Institute of Aerodynamics in Russia with Joukowsky in 1904, the first in Europe. He said in this regard that Lagrange, a man of great academic principles and pride, could not accept defeat. He had to develop a solution to Euler's equation. So here is Lagrange in his Mécanique analytique book, or Analytical Mechanics, 3 versions. He considered incompressible, so let's take rho equal 1 for the moment. Homogeneous fluid subject to forces x, y, z, such that this quantity is an exact differential. That is, the force come from scalar function, potential energy, V. Okay. In this case, he applies Euler's equations. And you can easily show that, okay, the left-hand side will be dp minus dv equals whatever we have here on the right-hand side. And you can see in the left-hand side, it's an exact differential. It's d of some function, which is p minus v. The right-hand side, he asked, how can I make it exact differential? So you can reorganize terms, and it's very easy to show that the right-hand side is equal to this term. Okay. Then he again asked, how can I make this exact differential? D of something. So he noted that if this condition is satisfied, u dx v dy w dz is an exact differential, so I can replace them with d of some function, say phi, then you can immediately realize that this is indeed d of partial phi partial t. And not only that, luckily, if this is satisfied, also these 3 terms will go away. In our own language now, these are the components of the local vorticity vector, the curl of the velocity vector. And if it comes from a scalar function, the curl is 0, right? So just by this assumption, everything now is set in place. Everything can be written as d of something. So we can collect all these functions, and we have d of some big function equals 0, which means that this function is indeed constant with respect to space. And this is, as you guys know, the unsteady Bernoulli's equation. And now you can see clearly it's not Bernoulli's, it's indeed Lagrange, right? He did not stop here. I mean, he liked this assumption that this is an exact differential. So he started to look at it into, more depth. And he arrived at what we call Lagrange's theorem. So he expanded the velocity distribution UVW in time in this form. So polynomial in time. And he said, well, he showed that if u dx v dy w dz is an exact differential, then the primes are also exact differential. And if the primes are exact differential, the double primes are exact differential, and so and so. And this implies that if u dx v dy w dz is an exact differential at some time t, it is so for all time, which means that the flow, if it started irrotational, it will remain irrotational. It will not lose this property. That's quite interesting. And this is actually the genesis of Helmholtz laws of vortex dynamics, that if you start a blob of fluid with some, vorticity, you will not lose it over time. And you cannot also gain. It stays the same. So vorticity just convect with the flow. It was quite interesting to see that in Stokes' seminal paper, 1845, we'll come back to it later. He didn't like Lagrange's proof. He had concerns. Look at this. He said, I think, succeeded in showing that Lagrange's proof of an important theorem, meaning this theorem, in the ordinary theory of aerodynamics is untenable. So it's not. He had concerns, and his concern was, if we say it in our own language, he's trying to say that this expansion assumes analyticity. So it assumes that UVW are analytic in time. It's a power series in time. And there's no guarantee for that. There might be square root t kind of thing. At any rate, the theorem is not wrong, but the proof, is flawed. So Stokes and even before Stokes, Cauchy, they both provided a more rigorous proof of the theory. Navier. So like I said, we have now mature fluid mechanics. We have equations of motion. We have particular solution. And to me, as a student of fluid mechanics, I always sit Navier very highly, in the sense that Navier-Stokes equations perhaps are the most important equations in fluid mechanics, right? They are our, if you want to say, Bible of fluid mechanics. Whenever we have a problem, we go to Navier-Stokes and see what does it say, right? It is the source of turbulence. It's the source of anything. We believe that it captures most of the phenomena of fluid mechanics, and it's the most important thing, right? And the first name that's associated with this very important equation is Navier. Unfortunately, when reading the history of fluid mechanics, this picture was spoiled a little bit, was ruined. Let's see why. So he wrote 3 papers to the French Academy of Science. One on elasticity, one on hydrostatics equilibrium, one on hydrodynamics. In the 3 papers, he proposed the molecular hypothesis. And this section is quite interesting. I'm going to go in detail. The molecular hypothesis is the following. He's saying, there is repulsive forces between molecules, so that when you apply external force, it's as if you have springs between molecules. So the spring will resist you back, and this resistance will depend on the relative distance between the molecules. So equilibrium will happen between, if balance occurs between the external forces and repulsive forces. And like I said, all the phenomena indicate that this repulsive molecular forces depend on the relative distance between molecules. So in his paper of the equilibrium of fluids, he considered 2 particles. Why am I going in detail, or a bit of detail, not very detailed, of his analysis? Because I did not find in any textbook of fluid mechanics it went to oblivion. People just ignored it. It's not as prominent as we think, you know, so you have to get it from the history, and I believe it's quite interesting presentation. It's very different from our own derivation of Navier-Stokes equation. So we have a particle m located at xyz, m prime located at x plus alpha, y plus beta, z plus gamma. So you simply get the relative distance between the two. Okay. Then he said, if m is displaced by what we call nowadays virtual displacements, right? Delta x, delta y, delta z, then m prime, remember these deltas, the displacements are function of the space. So m prime will be displaced differently, and you can relate delta alpha, beta, gamma to delta x, y, z and their space derivatives, right? Okay, then what really matters is the variation in the relative distance. And from this variation, you can get what he called moment of the mutual actions. In our language, it's the virtual work. Very simple, just multiply the force F by the virtual displacement, delta R, in the same direction. We're done. Integrate over all fluid to get the effect of all molecules on that particular molecule M. Very clear. And then you can, with very tedious mathematical manipulations, he showed that this virtual work, you can write it as follows. And because these terms will show up, you know, many times, I'm going to collect this integral and call it 2 term. So my term is this integral divided by 2. It's 2 pi over 3 times the integral. Okay. Now go and apply the principle of virtual work. So the virtual work, the first term here coming from the molecular forces, then the second term coming from the applied loads Fx, Fy, Fz, and this is my notation of the forces, just to be a little bit clear. So each force multiplying its virtual displacement in the same direction, and we're done. I mean, this is at equilibrium, so the virtual work is 0, right? Okay, now you simply do the usual trick of integration by parts and to arrive at the equilibrium equations. So you immediately get that Fx is partial term partial x, Fy partial term partial y, and so on. So these are nothing but Clairaut's equations of equilibrium, or Euler when you just drop the motion. It's just equilibrium. So when you drop the motion, just Fx is partial pressure partial x, and so on, so right? So indeed the pressure, our pressure to Navier is a measure of, you know, the repulsive or the molecular force. That's okay. So let's put this in perspective. So this is quite different from our derivation of the equilibrium equations. But if you do it this way, you get the exact same equations. That's fine. If you do it in motion, you will not get the exact same equations. So let's look at that. The same here, fluids in motion. He said, well, if it's in motion, we need to add new molecular force due to motion. And he assumed that this new molecular force will be proportional to the relative velocity between the two molecules. Makes sense? So this is the relative velocity projected on the line in between, m prime. So you can get it as follows. And then your virtual work will be, now this F is new F, is not the previous F, right? Because this is a new F due to motion, and the force is actually this F times the velocity. He said this is proportional to the velocity, right? The relative velocity. So you get your force times the virtual displacement, or here is the virtual velocity in the same direction, integrate to get the virtual work on the molecule M. And again, after very tedious mathematical manipulation, you arrive at that the virtual work is given by this bracket times this integral. And we're gonna call this integral to something. He called it epsilon. Okay, apply the principle of virtual work, assuming incompressible flow. So incompressible flow, we have partial delta x, partial x, delta y, partial y, partial delta z, partial z is, you know, is 0 from incompressible continuity, right? Apply the principle of virtual work and do the usual trick of integration by parts. You get this equation. The first part is Euler's equations of motion, and the molecular force hypothesis of Navier gives you immediately for free what we call the viscous action. There is no viscous, he did not account, there is no shear stress, there is no viscosity, nothing. It's just the hypothesis of molecular force. If you do it in motion, you arrive at this equation. This is very different from, you know, we are used to the two ways of deriving Navier-Stokes equations. One is the baby way or undergraduate way, which is actually Euler's way, a fluid element, you have pressure, you have shear, do the moment balance, you're done. Or the other way, the graduate version of it, the continuum mechanics version of it, where you do it continuum mechanics way, you assume Newtonian fluid, you assume isotropic, and you do it the continuum mechanics way. There is this, the Cauchy stress tensor, the deformation tensor, and so on. So this is the other way, right? This is neither. This is different. And in fact, the community didn't like his approach, and the community fought back. I'll show you here. Actually, Poisson, he endured very bitter criticism from Poisson, and they had I mean, their criticism and fight was published in the columns of the Annales in these couple of years. I'll show you just one of his responses to Poisson. So he's saying Poisson's equations, having come 7 years later, too late, might be said to be of the same form as the equations that had appeared first. In order to rob me of the merit of having given the differential equations concerned, it would be necessary to show that my principles are contradictory in themselves or with the natural facts. It's not sufficient to say that the same equations have been found in another way to claim without proof that this way is better than mine. So then Arago, the editor of the Annales, he settled this dispute to Navier actually. But the issue is that his equations went to oblivion. Nobody used it. Nobody continued upon them. And he got resurrected more than 20 years later by Stokes in the following way. So this is Stokes' paper. And in this seminal paper where he derived Navier-Stokes equations as we know nowadays in the continuum way. So I will not present anything about that. You can find it in textbooks. Look at this. He is now saying something like, this equation has been found before, right? I afterwards found that Poisson had written a memoir on the same subject, and on referring to it, I found that he had arrived at the same equations. The method which he employed was, however, so different from mine, like I told you. In particular, Poisson and Navier, they had one coefficient of viscosity, I mean, which we call coefficient of viscosity, one constant, right? One coefficient. Whereas I mean, the continuum way, if you have ever seen the continuum way of deriving Navier-Stokes equation, you have two coefficients of viscosity, right? The second coefficient of viscosity shows up. And as you guys know, in incompressible flows, the effect of this second coefficient of viscosity drops. So that's fine, but they are very different. And look at that. So during the entire paper, he keeps referring to Poisson, comparing with Poisson. And he just gave a small footnote here about Navier, that the same equations have also been obtained by Navier in the case of an incompressible flow. So this actually makes me wonder, should we name him Navier-Poisson-Stokes equations? At any rate, we're almost done with the first part. So Stokes arrived at the very rigorous proof of Navier-Stokes equations without the molecular hypothesis of Navier. And to do that, he couldn't do it without the contributions of Cauchy. Cauchy was a very interesting character. He actually occupied 3 prominent professorships of mathematics in Paris. He was among the elite. He could easily have been a member of the parliament, of the establishment of Paris, but he was opposing the political regime. So he was asked, when he was asked like anybody else to give an oath of allegiance, he refused, saying that he who does not respect his own conscience will never be respected by others. And actually because of that, Louis Philippe and his political regime, they forced him to leave the country. He left to Torino and then Prague to teach mathematics. Luckily he came back and by a special decree of the emperor, he was appointed to be chair of mathematics without giving an oath of allegiance. You know, he shows up as a shining star or shining example of academic integrity in the history of science. He published like more than 180 papers He is the one who derived the Laplace square psi equals 0 inviscid incompressible. He is the one of Cauchy-Stokes theorem, very important theorem in mathematics, that is applicable to fluid mechanics many times. Many of you are aware of it. Remember, we said, Lagrange derives Lagrange's theorem that an irrotational flow, if once irrotational, will remain irrotational for all time, and that Stokes criticized Lagrange's proof. Here is Stokes' paper. He is saying something about Cauchy's proof. I have mentioned the principles of Cauchy's proof, a proof I think liable to no sort of objection. So he's saying, it's an okay proof, a rigorous proof. Of particular importance that he actually studied the kinematics of deformation of a continuous medium, which is applicable to both solids and fluids. So Lamé used them in formulating solid mechanics equations. Stokes used them in formulating fluid mechanics equations. In particular, in this paper, he showed that the motion of a fluid particle consists of three types. Forward motion, the translation that we all familiar with. Then there is a deformation motion, linear, which he called linear dilatation or condensation. And what we call vorticity, he called it rotation. So the local vorticity, that we are very familiar with, we owe this concept to Cauchy. He is the first one to, formulate it. It's the curl of the velocity vector. Using these principles, like I said, Stokes used them, relied heavily on them to develop the equations of motion, as you guys know from continuum mechanics approaches. So let's recap. Archimedes, Da Vinci, Galileo forming mechanics, Torricelli's law and experiment, Pascal principle and Newton's Principia, Bernoulli's hydrodynamica, Dalembert paradox, Euler's equations of motion, Lagrange's integral, which is unsteady Bernoulli equation, Navier's equations of motion, Poisson's equations of motion, the same as Navier, Cauchy's work on the kinematics of deformation, Stokes culminating all of that to derive our most fundamental equations of fluid mechanics. A parallel line for the experiments, actually, Marriott, perhaps the first to measure forces on flat plates, Robbins and the concept of whirling arm, the experiments of Borda, Dubois, and Dalembert, Condorcet, and Bossuet, the committee of the Academy on the resistance of fluids, Poiseuille, and Reynolds. I don't know if we have time to go through Reynolds, perhaps yes. So, because it's very important in fluid mechanics. So I'll go here and do this. So in this 1883 paper, he actually, interpreted the du by dy kind of thing. And he is the one, proposing a definition for the coefficient of viscosity to be the shear force divided by this du by dy kind of thing, the rate of deformation. And he asked himself about mu a lot. Will it be different for fluid, different from a place to another, and so on. So he is very famous of this experiment. So we have a horizontal glass tube, and there is a dye coming here in the horizontal glass tube. So this horizontal glass tube is placed in this tank, has glass walls as well to see through. It's full of water. And there is a valve here. When you open this valve, you control the speed of the dye flow in the pipe. So at small speeds, you see just kind of almost stagnant flow. Laminar flow, just like this picture, and no change with time. It's just motionless picture. And you increase the speed further and further until some point, what we call now Reynolds critical speed. Eddies start to form, and there is diffusion. It's not like just a stream. It diffuses through the rest of the pipe. And if you do larger and larger speeds, it becomes chaotic and turbulent, and everything is unsteady. It's not stagnant anymore. And he showed by measuring the pressure, the difference in pressure head, or the loss in pressure head, he showed a measure of the friction coefficient of the fluid, how it varies with the velocity v. I'm not going to mention it now, but there is one important thing here that he noted, that you know what, if this ratio rho VD over mu is less than 1400, I don't observe transition to turbulent. And you guys know that this is simply the Reynolds number. This was the genesis of Reynolds number. Later on, Summerfield, he decided to call this ratio the Reynolds number. And this is the recap that we had with the experiment of Reynolds. This is the legacy that we had until this point. And the natural question is this mature or practical enough for flight? Do we need something more? What else do we need to enable aviation? These questions, are the motivational questions for next time. And let me stop here.